Welcome to the AI Checkpoints. Today we're diving headfirst into a topic that honestly sounds like sci-fi, but is becoming very real very fast. Self-evolving AI agents. Yeah, forget AI that just does stuff. We're talking about systems that continuously learn and adapt their own insides, their own components, literally upgrading themselves on the fly, almost like Alien. Like they get smarter with every single interaction. Living software, maybe? And our guide for this deep dive is some really cutting-edge research. We're looking at a big survey paper on Archive, the preprint server. Plus, it's GitHub repo. This is serious work from places like Google, Stanford, Berkeley, MIT, Tsinghua. So the big players, this is where things are heading.
Absolutely. And maybe before we jump into the evolving part, it helps to quickly nail down what a standard AI agent is, our baseline, right? So at its heart, it's an autonomous system. It uses a large language model, an LLM, as its, let's say, central brain. This brain understands things, plans actions, generates responses, all interacting with real-world environments. But it's not just the LLM. These agents usually have other bits too. Modules for perceiving stuff, planning steps, remembering what happened, and crucially, using tools like external APIs or databases. So it's a whole system, yeah, not just a language model in a box.
Okay, got it. A sophisticated system. But here's the burning question for me. Why do we really need them to evolve on their own? I mean, current AI is pretty impressive, isn't it? What's the big limitation here? What problem are these self-evolving guys actually trying to solve?
That's the perfect question. Because you're right, current agents are impressive. But the thing is, most of them are kind of rigid. They rely on static configurations. Someone designs them, sets them up, and that's pretty much it.
Like software you install and it just stays that way, unless a developer pushes an update.
Exactly, like that. And think about the real world. It's messy. It changes constantly.
Yeah.
User needs shift. New info pops up. New tools get released. The environment itself might change.
Right. Like a customer service bot needing to suddenly know about a new product launch.
Precisely. Or a science AI needing to use a brand new analysis technique someone just published. The survey paper makes this point really clearly. It says, despite progress, most agent systems still heavily rely on manual design and manually tweaking these things every time something changes. It's slow, it costs a lot of effort, and frankly, it just doesn't scale for these super dynamic real-world problems.
Okay, that makes sense. It's a bottleneck.
It really is. And that's exactly why this idea of self-evolving AI agents is taking off. The paper formally defines them as, let me get this right, autonomous systems that continuously and systematically optimize their internal components through interaction with environments, with the goal of adapting to changing tasks, contexts, and resources while preserving safety and enhancing performance. It's quite a mouthful, but the key words are continuously optimize and adapting.
Continuously optimize while staying safe and getting better.
Okay. And to guide this whole process, the researchers proposed something really interesting, the 3 laws of self-evolving AI agents, kind of inspired by Asimov's laws of robotics,
Oh, cool. Like a robot may not injure a human being.
Yeah.
What are the AI agent versions?
Similar vibe, but for self-improvement. So law 1 is endure. That's safety adaptation. An agent must stay safe and stable when it modifies itself. Safety first, always.
Makes sense. Don't break yourself while trying to get smarter.
Exactly. Law 2 is excel. Performance preservation. So, subject to Law 1, it has to keep performing its tasks well, or ideally get even better. Don't evolve backwards.
Right. No point evolving if you get worse at your job.
And Law 3 is evolve. Autonomous evolution. Subject to the first 2 laws, it needs the ability to actually optimize itself autonomously when things change. See the hierarchy? Safety is non-negotiable. Then performance. Then, and only then, comes the autonomous evolution. It's a framework for building trust, really.
Endure, excel, evolve. I like that. It really sets the guardrails. So this isn't just a tweak then. This sounds like a fundamental shift, a whole new paradigm in AI development.
Oh, absolutely. It's a major step. The paper lays out this progression pretty clearly. How we got here with LLM-based systems. We started with MOP model offline pre-training. Think of that, like building a car, rolling it off the assembly line, and that's it. It's trained on static data, deployed, and then it's frozen. Fixed.
The standard model we mostly see now.
Pretty much. Then came MOA model online adaptation. This is where models can be updated after they're out there. Things like fine-tuning or that RLHF reinforcement learning from human feedback.
Like getting software updates for your phone. It gets better over time, but someone's still pushing the updates.
Exactly. It's reacting to external input. Then we got MAO multi-agent orchestration. Now we're coordinating teams of agents They talk, they collaborate on complex tasks. But crucially, the individual agents themselves aren't really changing their core programming. They're just working together in a fixed structure, like a well-rehearsed orchestra.
Okay, so teamwork, but the players stay the same.
Right. And now we're at the edge with MASE multi-agent self-evolving systems. This is the really wild part. Here you've got groups of agents that are constantly refining themselves. They tweak their own prompts, how they use memory, their tool strategies, even how they talk to each other. And they do this based on feedback from the environment and these things called meta rewards. Basically, getting rewarded not just for doing the task, but for how well they learned and adapted while doing it.
Wow. Rewarded for getting smarter.
Pretty much. It's the vision of true lifelong learning AI. The paper uses this great phrase, AI that lives, learns, and lasts. It's a jump from just executing to actually evolving.
Lives, learns, and lasts. That's powerful. So we're moving from tools to something more like digital organisms. Okay, so how? How do they actually do this continuous self-improvement? What's the mechanism? What's under the hood?
Right, the how. It's essentially framed as an iterative optimization loop. Think of an athlete trying to improve.
Okay, like a basketball player.
Yeah, perfect. The player, that's the agent system, wants to get better, the task. They practice, that's the optimizer in the gym, the environment. They get feedback maybe from a coach or watching replays, evaluation metrics. And then based on that feedback, they adjust their shooting form or their defensive stance. That's changing the agent's configuration. It's that cycle. Act, get feedback, adjust, act again.
A continuous improvement cycle.
Exactly. And that optimizer part, the coach, in our analogy, it has two main bits. There's a search space, like what things can the athlete actually change? Their stance, their grip, their diet. For an AI, it's things like prompts, memory strategies, tool use. And then there's the optimization algorithm. How do they make those changes? Do they try random stuff? Do they make small adjustments based on feedback? That's the strategy for finding better configurations.
Got it. Search space is what can change. Algorithm is how to change it.
You got it. So let's dive into some specific techniques, starting with just a single agent improving itself. Single agent optimization. A huge area here is prompt optimization. We know LLMs are super sensitive to how you ask them things,
Yeah.
right? The exact wording matters a lot.
Oh yeah, prompt engineering is practically an art form now.
It really is. So these systems are learning to optimize their own prompts. There are a few ways. Some use edit-based methods, like having an AI editor that tweaks a human-written prompt, making small changes to improve clarity or effectiveness.
Iterative refinement.
Yeah. But then you have generative approaches, which are cooler, I think. The LLM itself actually generates totally new, potentially better prompts based on performance feedback. It's not just editing, it's creating.
So the AI is writing its own instructions.
Kind of, yeah. Then there are text gradient-based methods. This borrows ideas from how neural networks learn. Imagine getting feedback that's not just good, bad, but more like a direction. Make this part more formal, or emphasize this keyword more. It's using language itself as a signal to guide the update.
Like nudging the prompt in the right direction using words.
Exactly. And finally, evolutionary techniques. These treat prompts like species in biology. They generate variations, mutations, test them out, and the best performing ones survive and reproduce, generate more variations. It's literally survival of the fittest prompt.
Wow, natural selection for prompts. That's wild.
It is. The point is, the AI is getting better at talking to itself, finding the best ways to frame tasks and instructions. Okay, next up, memory optimization. This is critical, especially for long tasks or conversations. Agents need to remember relevant stuff and not get lost or start making things up hallucinating.
Right, keeping context over time.
Yep, so there's work on optimizing short-term memory managing info for the current interaction, maybe by summarizing or selectively forgetting less important details, and long-term memory optimization building persistent knowledge stores across many sessions, remembering user preferences, past successes, accumulated facts, making the agent truly knowledgeable over time.
Building a history.
Exactly. And then there's tool optimization. Agents are powerful, but they're way more powerful when they can use external tools, search engines, code interpreters, databases, specific APIs.
Extending their reach beyond just the LLM.
Right. So optimization here involves learning how to use these tools effectively. Some approaches involve training the base LLM, showing it examples of good tool use or using reinforcement learning. Others focus on inference time optimization. This is about improving how the agent decides which tool to use and when during a task. Maybe it refines its understanding of the tool's documentation on the fly or uses complex reasoning, like planning out a sequence of tool uses.
So it's not just having tools, but becoming a skilled user of those tools.
Precisely. Becoming a master craftsman, not just someone handed a hammer.
Okay, that's a lot for just one agent.
Mm-hmm.
What about teams? You mentioned MAEs, multi-agent self-evolving systems. How do teams of these agents learn to get better together?
Good question. That takes us to multi-agent optimization. And yeah, using teams of agents has big advantages. They can tackle way more complex problems, work in parallel, be more robust if one fails. Others can maybe pick up the slack, and you can get richer solutions from different agent perspectives.
Makes sense. Diversity of approach.
Right. And the really cool optimization happening here is moving beyond humans manually designing how these agents talk to each other. Instead, we're seeing topology optimization. The system itself figures out the best communication structure, which agents should talk to which other agents. Maybe some communication links are unnecessary or even risky. Some systems can automatically prune these connections for better efficiency or safety.
So the AI team learns how to organize itself for the best results.
That's the idea. Self-organizing communication. And finally, all these optimization techniques aren't just general, they're being applied in specific areas. That's domain-specific optimization. Like in biomedicine, you see multi-agent systems simulating doctor consultations for diagnosis, integrating medical knowledge bases, or agents using specialized chemistry tools for drug discovery, learning from simulated experiments.
Tailoring the evolution to the specific needs of the field.
Exactly. In programming, agents are learning to debug code by actually running it, looking at the errors, and correcting themselves. Self-debugging code. And in areas like finance and legal research, agents are being optimized for super precise reasoning over structured data, maybe simulating legal arguments or doing complex financial analysis, adapting to the specific rules and data types of those domains.
It's really about making them not just generally smart, but expertly adapted to particular complex jobs.
Precisely. Adaptable expertise.
Okay, this is incredibly powerful stuff. The potential seems enormous, but the saying with great power, how do we make sure these things stay safe, that they stay aligned with what we want them to do, especially if they're changing themselves? This goes back to that first law, right? Endure.
Absolutely critical. And that's where evaluation becomes even more important and more complex for self-evolving agents. People talk about LLM as a judge, using one AI to evaluate another's output. It's fast, scalable.
But I've heard it can be biased or easily fooled, depending on how you prompt the judge.
Exactly. It has limitations. So a more advanced idea is agent as a judge. Here, it's not just an LLM checking the final answer. It's a whole agent system evaluating the entire process, the reasoning steps, the tool use, the whole chain of thought.
Looking at the how, not just the what.
Right. It's potentially more aligned with human judgment, maybe more robust, but it's also more complex to set up. And the key thing, the really crucial part for self-evolving agents, is that this safety evaluation can't be a one-off check before deployment. It has to be dynamic and continuous. As the agent changes itself, the safety checks have to keep up.
An ongoing safety audit, essentially.
Something like that, yeah. It has to be part of the evolution loop itself.
So looking ahead, what are the big hurdles? The researchers identified key open challenges, right? Grouped by those 3 laws.
They did. Under endure safety, the big challenges are, well, ensuring that safety robustly as the agent changes, keeping up with changing regulations automatically, making sure the agent's evolving goals stay aligned with ours, and dealing with potentially unstable reward signals. If the thing guiding the learning keeps shifting, it's hard to learn consistently.
Tricky. What about Excel? Performance.
Big challenge there is evaluation, especially in areas like science or law where there isn't always a single right answer or ground truth. How do you measure better performance? Also, balancing performance with efficiency, these agents can be really computationally hungry. And making sure the optimizations aren't too brittle. Does a perfectly optimized prompt for one model work on another? Or does it break? That's generalization.
Right. Avoiding over-specialization.
Yeah.
And evolve.
Yeah.
Autonomy.
The challenges there are pushing beyond just text, handling images, audio, video multimodal input, adapting to the physical world, not just digital environments. And maybe the biggest one, getting agents to not just use tools, but to autonomously discover the need for and maybe even create new tools when required.
Wow, inventing their own tools.
Yeah.
That's a major step towards real autonomy.
Huge step. But these challenges also point to where the research is going. It's incredibly exciting. Researchers are building sophisticated simulated environment, think advanced digital playgrounds, where agents can practice evolving safely and quickly.
Digital gyms for AI evolution.
Kind of. There's a massive push on tool use and creation. Going beyond just calling APIs to agents that can figure out they need a new capability and potentially build it, or combine existing tools in novel ways. We also need better benchmarks. Not just static tests, but dynamic long-term evaluations that really track adaptation over time in realistic scenarios. And making it practical, designing optimization algorithms that explicitly factor in resource constraints. How much computing power, how much energy, how much money does this evolution cost?
Balancing power with practicality.
Exactly. And finally, really doubling down on tailoring these methods for specific domains like science and medicine, embedding expert knowledge, and handling things like regulatory compliance right within the evolution process.
So it sounds like the path forward is challenging, but the direction is clear.
Very much so. It's a challenging but incredibly exciting frontier.
Well, that really brings us full circle, doesn't it? This journey from static AI to these truly self-evolving agents. It feels like it's paving the way for AI that isn't just powerful, but genuinely adaptable, resilient, and capable of learning throughout its lifetime in our messy, changing world. Building AI that can truly endure, excel, and evolve. If you found this deep dive into self-evolving AI agents as fascinating as we did, definitely hit that like button and subscribe for more insights into the absolute cutting edge of technology. See you next time on the AI Checkpoints.